This is day 2 of our second packet, and our second packet is going over common graphs. And so we're going to start by looking at vertical stretch versus vertical compression, things you've learned about dating back to freshman year. Vertically compressed graphs take the same x values of the original function and map them onto smaller y values. So if we say f of 1 is the original function, then we can look here, and if we have a value in front of the original function that is between 0 to 1, this means it's vertically compressed. How else could we describe this? This new function that is now vertically compressed, it's compressed by a factor, it's vertically compressed by a factor of a, that's the number outside, that's in front, that's between 0 and 1. And it's compressed towards the x-axis of the original function. So let's take a look here and let's graph it on a nice graph that I have prepared. So let's start, let's say this is our original function. So I'm going to graph this original function coming up with some x and y values. Let's start with 0. 0 minus 1, this is original function. 0 minus 1 is negative 1. Negative 1 squared is 1. Let's go to 1. 1 minus 1 is 0. 0 squared is 0. Let's go 2. 2 minus 1 is 1. 1 squared is 1. Notice this. If I go to 3, 3 minus 1 is 2. 2 squared is 4. Now watch this. If I go up to negative 1 and negative 1 is negative 2, and negative 2 squared is 4. So let's go ahead and graph this parabolic shape. Alright, so I'm going to go 1, 0, 1, 0, and then I'm going to go 0, 1, negative 1, 4, and the opposite way, 2, 1, and 3, 4. 2, 1, and 3, 4, and we can see this is the original function. Original function. Now, what happens when we take and we put a value out front of this function that is between 0 to 1? So this is an example of vertically compressing it. So what we're gonna do is we're gonna take the same x values, but our y values are gonna become closer and closer to the x-axis. So I'm gonna write down the exact same y values. And now what happens is we take the original output of our function, we take it times 1/2. So half of 4 is 2, half of 1 is 1/2, half of 0 is 0, half of 1, and half of 4 is 2. I'm going to graph that with a different color here. So negative 1, 2, negative 1, 2, 0 and a half, 0 and a half, 1, 0, 2 and a half, and 3, 2. 2 and a half, and 3, 2. When it's compressed, vertically compressed, it's flattened out towards the x-axis. Let's talk about if something is vertically stretched. Let's talk about if something is vertically stretched. What would that then look like? So in much of the same ways, we're going to take the exact same x values from the original function, and we know it's vertically compressed when this value up front, this numerical value, is greater than 1. What if it's equal to 1? If it's equal to 1, it's neither stretched or compressed. So we're going to take this original function, and what we're going to do is I'm going to put a value greater than 1 in front. So let's take this right now. We know this was the original function. It was x minus 1. This is the original. And we're going to square that. Now we've done a 1/2. We can see how it flattened out or vertically compressed. So it's what it's been done is being pulled towards the x-axis. Watch when I put a number out front that is greater. Let's try a number like 3. What happens when I put a number like 3 out front? So I'm going to take this and I'm going to go back to, if I pull this down here, we're going to come back to these in just a second. But let's say this is our original. So our original, if I go back here, this is our original right here. This is an example when we compressed it. I'm going to say f of 3. F of 3 is the original function right here, and what we've done is we're going to put a 3 in front. So we're going to vertically stretch this by a factor of 3. So I put down the exact same x values, negative 1, 0, 1, 2, and 3, but now the original outputs are going to be multiplied by 3. So this is not 4, it's 12. This is not 1, it's 3, 0, 3, and 12. I took the outputs, the y values, times 3. And I wish I had a different marker. Let me press pause and see if hopefully it shows up here. And so what I'm going to do now is I'm going to take those values. Let's start with negative 1, 12. So negative 1, 12, 2, 4, 6, 8, 10. So 12 was way up here. And we have 0, 3, 0, 3. And we have 3, 12. So the original function is going to be the purple function. This function that is shown in pink is going to be vertically compressed by a factor of 1/2, and what we have in blue is going to be vertically stretched by a factor of 3. The x values in every case remain the same, but the y values are impacted by it being a stretch or a compression. And once again, how do we know whether it's a stretch or a compression? If the value in front is between 0 to 1, we say it is vertically stretched, okay? So that's going to be, it's going to be pulled higher off the x-axis. And if it's, let me go back here. It's vertically compressed, so it's going to be pushed down towards the x-axis. We can see pushed down towards. If it's vertically stretched, so a is greater than 1, it's going to be pulled further away from that x-axis. Another one here, so let's go back to this example right here. And I'm going to make up just the very basic of it. So this is the original function, f of 1. So when I think about that, what's the smallest number I can plug in? I can't plug in negatives and get outputs that are real numbers, so I can plug in 0. Square root of 0 is 0, square root of 1 is 1. Now 2 and 3 give me irrational numbers. Square root of 4 is 2. 5, 6, 7, 8 give me irrational. Square root of 9 is 3. So I'm going to graph that. 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, and 9, 3. So there is our function. Now what happens when I see the value of 3 in front? When I see a value of 3 in front, I know right away it's going to be vertically stretched. It means it's going to be pulled away from the x-axis. It's going to rise at a faster pace. Vertically stretched by a factor of 3. So each of these values is going to be multiplied by 3. So instead of 0, 0, well, 0 times 3 is still 0. Instead of being 1, 1, it's going to be 1, 3, because 1 times 3 is 3. So 1, 3. Instead of being 4, 2, 2 times 3 is 6, so 4, 6. And lastly, it's going to be 9. Take this times 3, 9, 9. And this is a great example, again, of being vertically stretched. It's going to be pulled away from, vertically stretched is being pulled away from the x-axis. If I just had to draw a picture of what something would look like if it was vertically compressed, that a value in front of the function is going to be between 0 and 1. So if I took this original function in blue and I took 1/2 of it, then what I want to do is I want to take the outputs and cut them in half. Half of 1 is 1, half of 2 is, half of 1 is 1/2, half of 2 is 1, half of 3 is 1 1/2. So the purple would be vertically compressed by a factor of 1/2. I'm going to go over horizontal stretch and horizontal compression, which may be new for you. So I want to slow that down and use in-person instruction for 0 hour as I go through this. All right, let's look over these dilations. So writing an equation of the function g of x whose graph is a dilation of the graph defined by y equals f of x. Okay, so what I'm going to do is I'm going to take g of x, and what I'm going to do is I want to dilate f of x. So take f, and wherever I see a variable in function f, I'm going to place a 2x. I come back here, g of x is going to be equivalent to whatever f is, here's f, but place a 2x where there's a variable. So 4 times 2x plus 7, 8x plus 7. Okay, in example number 2, same concept. I'm going to take g of x and I'm going to put a 4 in front of the function, in front. So it's not going to go inside with the x. Notice how it is in front. So here we go. Here is the function f of x, and I'm putting a 4 in front. In the last example, I have f of x equals x squared. For g of x, Notice how the 1/2 is inside with the x, not in front. So I'm going to write down the function f of x, which is right here, but instead of just having an x, I'm going to put a 1/2 x, and notice it has to be squared, which means I'm going to take it times itself. 1 times 1 is 1, 2 times 2 is 4, and I have x squared. Right, so if we're looking at these particular problems, suppose the graph of the function g of x is the dilation of the graph of f of x. If the given point is on the graph of f of x, give the corresponding point on the graph of g of x. So remember, we're going to have the same x values. It's going to have the same x values here. So what am I doing? All right, so if I plug in 2 here, let me press this pause here. Okay, so for this particular problem, notice that the 16, the change here is that we have the 16 now that is out front. The 16 is that vertical factor, that vertical stretch. And so what's happening here is that when I plug in a 2 to the third, 2 times 2 times 2 is 8. 1 over 8 is going to be the outcome, or the output. Input 2, output 1/8 for f of x. Then let's do the same for g of x. So I have a 2. 2 to the third, 2 times 2 times 2 again is 8, so 1 over 8. But this time we have a 16 out front. So on the graph of g of x, 16 times 1 is 16, and 16 divided by 8 is 2. Let's go on to the next example. For the function f of x, when you substitute a -9 in, the opposite value of -9 is +9. This goes to f of x as it's stated up above. Now let's do the same for g of x. Now notice the 1/3 is inside with the x. So when I plug in a -9 here as the input for g of x, -9 times 1/3, well, -9 times 1 is -9, divided by 3 is -3, and the absolute value of -3 is +3. Now just look at this output here. We went from 9 to 3 for the output. The x's remain the same. We went from 9 to 3. If I take 9 times 1/3, I get 3. Looking over here, I went from 1/8 to 2. If I take 16 times 1/8, I end up with 2. Before I go do this, I want you to pull up on your computer or on your phone here. Let's make sure I have this set. Hold on. I want you to pull up right here. So this was put into a Teams page, and it's going to describe to us whenever we see a vertical translation. So we're going to go up or we're going to go down. We're going to be adding behind the function generally. It could be in front, but behind generally is where we see it. We're going to add or subtract. Down is going to be subtracting, and adding is going to be going up. Now for a horizontal translation, remember we do the opposite. So if we're going to go to the left, it's plus, and if we're going to go to the right, it's minus. Sometimes students need to really look at these again. So when we are going to reflect across or over the x-axis, the negative sign is out front. But when we are going to reflect over the y-axis, the negative sign goes inside. And then we can see the vertical stretch and the vertical compression down below. Let me erase this here as we look at our next example. Okay, I want you to take a look right now at this first example, and I want you to fill in what, and the order doesn't matter, what do you think is happening from this function as it transforms into g. First, let's look here, and let's do just what we look at here and go one after another. I'm going to start with the transformations of vertical and horizontal transformations or shifts. So when I look at this graph, I can see that instead of saying going to the right one, we're going to go to the left 1 unit, and we're going to shift up 3 units. Now in front, these are 2 separate things. The negative sign in front, if I come back here and I show you, notice that when the negative sign in front, we're going to say a reflection over or across the x-axis. All right, a few more to look at here. So with the negative sign, it's separate than the 2. This negative sign is like a -1. And as I just showed you, the negative sign out front right here is going to reflect, is going to show a reflection across or over the x-axis. Now, the 2 is different than the negative sign. A number out front is going to represent, if this number right here, it's separate than the negative sign. If this value is greater, so this is an a value, if it is greater than 1, we say it's a vertical stretch. If this a value would be greater than 0 but less than 1, it would say a vertical compression, which means it gets closer. The x values stay the same as our original, but the y values get closer to the x-axis. So 2, not negative 2, just 2, is a vertical stretch by a factor of 2. Now what about that 1/5 on the inside? Remember, I'm going to go over horizontal stretch and compression in class tomorrow, but I do want to show you this. So notice that it's x over a number, x over a number, x over a number. So if you are left with a fraction, if we're left with a fraction here, we are going to be told, here we go, b, it's next to the x here. If b is greater than 1, it's a compression, so it's just opposite of above. And for the horizontal stretch, if b is between 0 and 1, we say that it is a stretch. So notice how the b value goes underneath, so it's like 1 over b, 1 over b, okay? So let me press pause and come back to our picture. This value out front is 1 over 5. It's 1 over 5, and 1 over 5 is like 0.2. 1 over 5 is equivalent to 0.2, so I'm going to go back to that picture. So 0.2 or 1/5 is between 0 to 1, so that's how I'm able to say that is a horizontal stretch. So I come back here and it says horizontal stretch, and then the value is going to be the number that's on the bottom. So in this case, it's horizontal stretch by a factor of 5. So it's 1 over that number. I want to show you again. 1 over that number, we can see this right now. See that b is on the bottom, so it's 1 over 5, 1 over 5. And again, why did I choose to say stretch? Because 1 over 5 is equivalent to 0.2 here. Let's look at the next one. Right, for this one, I see that in the x position, we have transformed it and we have an x minus 2. So we're going to shift horizontally to the right 2 units. Shift horizontally to the right 2 units. Now look at, we went from -2 and now we're up to 10. So I took this original function and what did I have to add to it? What numerical value did I add to -2? So -2 plus what value gives me a 10? I must have added a 12, so I added a 12. Well, if we're added behind it, when we add behind it, notice up here when I add behind it, it's going to be a transformation of a vertical transformation or a vertical shift up. So I'm going to shift up 12 units. Okay, let's start with the obvious here. So the obvious is inside from this original function. I am going to say not move to the right horizontally 1 unit. It's going to be horizontally shift to the left 1 unit. And it may help you then to cross that out. And we're going to vertically shift down 2 units. Okay, got that. And remember, when there's a negative sign out front, it's going to be a reflection across the x-axis, and this value that is between the negative sign and part of my original function here, because the 6 is greater than 1, it's going to be a vertically stretched. So don't just say stretch, because it could be horizontally or vertically. Vertically stretched by a factor of 6. So I want to go and I want to compare this problem where in this position I have a 3 and here I have a 1/5. Now both of them are embedded within this original parent function. But look at when I have 1 over a value, we say vertically or horizontally stretched by that value on the bottom. Here I have a value, so it's going to be horizontally, but is it stretched or is it compressed? If I come back here, it needs to be 1 over whatever that value is, 1 over that value. So 1 over some number equals 3. What number can I divide by and I get 3? I'm going to put an x there. What number can I divide by and I end up with 3? What number can I divide by and I end up with 3? Well, if we cross multiply, I have 3x equals 1 divided by 3 divided by 3, and I get x equals 1/3. X equals, start taking time to write it out, we have horizontally compressed by a factor of 1/3. when this number inside, so it's embedded within the problem, not on the outside, when this value here is going to be not a fraction or horizontally compressed. So it's 1 over that number. Up above, when I'm left with a fraction inside, embedded within this, not on the outside, within it, the number on the bottom is going to represent the factor which it is horizontally stretched by. Pretty confusing. We'll go over it again. Okay, so let's get started here with this problem. So I'm going to shift up 5 units. I've taken care of this. Now notice that there's a negative sign in front. When the negative sign is out front, it's a reflection across the x-axis. When the negative sign is put in front of the variable within the problem, it's going to be a reflection across the y-axis. Taking care of that. Plus 4 doesn't mean move to the right 4. It's going to be a shift to the left 4 units. And lastly, we have a number up front. Remember, when this a value is greater than 0 and less than 1, it's going to be a vertically compressed by a factor of 1/2. Okay, press pause, try the very last one. The order in which you do these doesn't matter, so I'm going to start here, and to save time, I'm not going to write them down. You will have to. So what does this mean? You're going to shift down 2 units. Again, the order you do these in doesn't matter. This, because we have a negative sign that has gone out front, is going to be a reflection over the x-axis. The number 7 is greater, it's your a value, it's greater than 1, so it's going to be vertically stretched by a factor of 7. We got a negative sign in front. It's going to be a reflection over the y-axis, and right here we are going to horizontally shift to the left 6. Topic handwriting. Let's see if you could go ahead, take this information, and if you could create a function. Go ahead, create a function with the following transformation. So what does g of x look like? If g of x takes f of x and it uses this transformation, what does it look like? So reflected about, or it should have been over, reflected over or about, I guess they could say, reflected over the y-axis is how I prefer to say it. And if that's the case, then I'm going to take this value, I'm going to have 1 over negative x cubed. Okay, so I've got that. Shifted 7 units to the left. So instead of going -7, it's opposite. We're going to go +7. 2 units down, -2. Vertically compressed by a factor of 1/5. So in front of all of this, I need to multiply by 1/5. Okay, last one for this quick lesson. Read this, press pause, and see if you can create, let's call this f of x. If you can create the function f of x based on this original. Alright, so here we go. We are going to reflect about the x-axis, or over the x-axis as I prefer to say it. Done. So that's going to be in front of this function. And then we are going to shift up 3 units, +3 is in back. And vertically stretched by a factor of 4, 4 goes in front. Video number 1, you were asked on this particular packet, you were asked to complete 1 through 26. This is video number 2, and I'd still like you to try them all, especially now that we've worked a little bit more with horizontal stretch and compression, horizontal stretch and compression. But we're starting here on number 27. Know that I'm going to start off class by doing 27 through 31 with you, because I would like you to try them in advance, and then I'd like you to go through the remainder of this packet and finish on problem number 45.